Good morning, everyone. Welcome to today's CIS seminar. It is my distinct pleasure to welcome and introduce today's speaker, Dr. Andy Nonaka from Lawrence Berkeley National Laboratory. Andy got his bachelor's degree in electrical engineering from the University of the Pacific in California, and then did a PhD at UC Davis in engineering and applied sciences. And already during his PhD, he started working at Lawrence Livermore National Laboratory and then later moved to Lawrence Berkeley, where he has been since. And he runs a group and he runs the Center of Computational Sciences and Engineering, a group that works with a lot of applied sciences and research scientists on working or making high performance computing possible. So one library framework they developed is the AMReX software framework for extreme scale science, which can be used across many different disciplines, and I'm sure Andy will tell us a lot about that today. I just want to mention one thing. The Warp-X code is one example of a code that uses the AMReX software library, and it won the 2022 Gordon Bell Award. So that's a major achievement in high performance computing. It was a team involving people from France, Japan, and from Berkeley Lab. And they got scaling on at least 4 different supercomputers. So it demonstrated the performance portability and the scaling capabilities of this software framework. So I'm very much looking forward to your presentation, and I'll hand the floor over to you.
Okay, thank you all. Thanks for inviting me, having me out here. I've never been to Delaware before, so this is fun. Thanks for everyone for coming. So okay, I'm Andy Nonaka. I'm the group lead for a group called the Center for Computational Sciences and Engineering at Berkeley Lab. I'm going to talk about one of the main things our group does, which is development of this AMReX framework, and by extension, lots of different applications that are based around it. So let's get going. Okay, so what overview of my talk? I'll give a brief introduction since it's the other side of the country in a whole different world at times. Berkeley Lab, what our group is all about. I'm going to talk about something you may or may not have heard about that recently ended called the Exascale computing project and how that relates into what we've done. I'm going to spend a lot of time talking about all sorts of different applications we have been and are presently involved with in terms of just general algorithmic features of what software does as a nod to, because we all must. How does AI and ML play into all this? And that's been increasingly so over the past few years. So the last maybe third to quarter of my talk will be about AI ML stuff. So I know that's very relevant to this department, reading about bios of faculty and people here. So this is kind of a touch it all type of talk where I'm going to talk about a lot of different things and not go very deeply into anything. Please interrupt with questions. And if you want me to talk in more detail about something, please come talk to me after, because I'm literally going to try to touch as much as possible in terms of application and what the software can do. Hopefully there's something of interest to everybody here, whether it be application space or something about computer science. So there's going to be a lot here. So I'll do my best to leave time at the end for questions as well. So first off, okay, we're all the way across the country here. Berkeley Lab. So the Department of Energy has 17 national labs. Berkeley Lab is one of them. We're the oldest one. We were established 1931 by Ernest Lawrence. Most of our funding comes from the Department of Energy, but we'll take money from NSF or any other program at our office. But I would say the grand lion's share of the funding that comes into our lab is colored by the Department of Energy. So you may have heard the word Lawrence before. About half an hour down the street from us, in the city of Livermore, there's a lab called Lawrence Livermore National Lab, which is much, much more famous than us because they're a nuclear security lab. They're in the news a lot, especially locally. There's an annual protest. People don't like a lot of what they do because they think it's bad because it's weapons, but we are not that lab. Lawrence Berkeley Lab is a completely open lab where there's no classified information. In fact, you can see on the map on the right here, on the left, that's the lab, and what I have circled below is the actual UC Berkeley campus. So we feel like campus. If you are a campus student, you can share your campus ID and ride the bus and come up to the lab. There's no security in terms of classified material only. So we feel very much like a campus. There's a free flow of students to and from campus. A large percent, if I had to guess, maybe upwards of a quarter of the staff in computing sciences have joint appointments where they are actually professors at UC Berkeley and researchers at the lab. But the lab itself has about 4,000 employees. It's a basic science lab. There's lots of things going on, such as biosciences, earth sciences, environmental sciences, energy sciences and technology, physical sciences. So computing sciences, we are one of only 6 areas at the lab, and it's pretty evenly distributed amongst those 4,000 employees. So what do we do in computer sciences broadly? There's a supercomputer facility called NERSC, which houses Perlmutter, which I think when it was first turned on 4 or 5 years ago was number 6 or number 7 top supercomputer. I think it's down to number 14 now. So ESNet is a national network maintained, run by the Department of Energy. And then there's research divisions, which consists of applied mathematics efforts, computer science efforts, and data research divisions. So within computing sciences, there's about 50 groups, and my group is just one of them. So that's the scale of what we're talking about here. My group has about 15 staff or postdocs, and we love our summer visitors. Dr. Schiller has visited us twice, along with Nikhil. Our group houses probably more than anyone else, where we maybe have 20 annual summer visitors a year. So we love it. We have the best view of anywhere. You can see on the bottom right, we're elevated, we're above Berkeley. So we see down into the city of Berkeley, Oakland. You can see across and see the Golden Gate Bridge right outside my office. There's San Francisco on the left. So, you know, we're kind of renowned for the views up there too. So we got the good real estate. Okay, Exascale computing project. That was a very, very big deal. It was a project that the Department of Energy funded, and it lasted until just the end of last year, from 2016 to 2023. Broadly speaking, they wanted to develop an exascale computing ecosystem for science. The total funding over the project was on the order of almost $2 billion, and from their website, almost 3,000 people across the DOE complex were funded by this effort at one point. I would say 2/3 of our group during its peak was funded by exascale computing. So just within our group at that time, we may have had 20 people that were working on this project during that time. So what came out of this project was exascale computing ecosystems, including the hardware, software, and applications. The scientific impact was now we have this ecosystem where we can run on one of the 3 big DOE supercomputing systems. All sorts of software algorithms and applications were developed based off of this. And even though the project is over, the remnant of it, we still work with a lot of application teams on scientific partnerships. And the main thing about this is at the very bottom, you can see the word GPU. Now, notably, AI/ML wasn't as huge of a thing during this initiative, but DOE is now really, really pressing hard on this. So AI/ML is becoming part of everything, where it was only a part of this. But I'll get to how we relate to AI/ML kind of at the end. So what our tiny role in this was, our group was the home to what they call a co-design center. And we were in charge of developing a block-structured adaptive mesh refinement algorithm. Now, the PIs for this particular subset of the project were John Bell and Ann Almgren in my group, and the lead developers of the actual infrastructure framework, Wade Chen, Andrew Myers, and Gene Sexton, were also scientists in our group. The primary products that we developed over this time period was this open source framework called AMReX, and it's primarily C++, although I will talk about Python and Fortran a tiny bit later. But not only were we in charge of developing this AMReX framework, we had to work with scientific teams to develop specific application codes that were supposed to run with this. So I'll talk about what adaptive mesh refinement is and what a lot of these application codes were in the forthcoming slides. But the bottom line is there's 3 big machines in DOE. There's Perlmutter, Frontier, and Aurora. They all have different GPU types and different multi-core architectures. And the goal was to have this software to be able to run at scale on all of these things. So Perlmutter's the smallest of the 3, has on the order of 2,000 GPUs, whereas Frontier and Aurora were much bigger, different GPU types on the order of 40 to 50,000 GPUs. So as I mentioned, we had a very diverse team just within our group working on this project, from software engineers to applied mathematicians, such as myself, to the actual domain scientists who knew actually the science. So AMReX at its simplest level, we solve partial differential equations on structured grids. So if you've taken any kind of numerical methods course, some of the basic methods you studied were finite difference and finite volume methods. So on the right, you can see an image. You have a computational domain. You chop it up into regular cubic or cuboid grid cells. You have variables such as rho, u, and e, which could be density, velocity, or energy of a system. And you assign a value of each of those variables to each grid cell. And then you use applied mathematics to develop numerical solvers to advance equations in time. So at the simplest level, AMReX handles this. And at that simple level, it's just multidimensional arrays. And you can solve equations such as Navier-Stokes, Maxwell's equations. You pick and choose any of your PDE to solve your problem of choice. And the basic Sussman procedure, as I mentioned, you divide up your domain, you assign values, and then you use a numerical method to solve the PDE. So at the basic level, it's something you could write up in MATLAB, Python, C++, just make a multidimensional array. And you could do this at a small scale, just in any programming language you want. But the magic of this is, okay, PDEs describing the real world applications that the DOE funded are actually quite complex. So even some of the mathematics for how you would solve these things numerically is not well known. There's lots of terms in these things. They're really highly coupled. You need to be able to resolve large spatial and temporal timescales in one simulation sometimes. Even with a supercomputer, that can be expensive to run simulations out for, you're running some weather model and you need to run for weeks at a time. It doesn't run in an hour even on a supercomputer. You still need to run it maybe for days or weeks. You need to run lots of ensembles of simulations because you can't just run one big simulation and claim you've solved something. I've noticed science tends to happen the way we do it. We like running medium scale simulations, but lots of them so we can vary parameters and see how it affects the output or do statistical ensembles of things. Another problem we have is that if you're doing a structured mesh, how are you going to do something with geometry? I just showed squares on the screen. Another thing is we care about how particle data structures can be used for simulation as well. Then you get to the aspect of, I want to go big. So how do I parallelize this code if I want to run it on 40,000 GPUs? And on top of everything, how do I make this really easy to program so people like me, I'm not a computer scientist, I'm an applied mathematician, I can use this AMReX software that the computer system engineers in our group have developed to write application codes, because I like interfacing more with the domain scientists to write code. So how do they make this easy, being that I am not an MPI, a CUDA, or a HIP programmer, but I'm gonna be able to do this. So just to give you an idea, what can you do with this? So there were 6 specific applications that came along with the ECP task that we were asked to work on. And you can see there they are. They all have the word Exa in them to make them sound really fancy, but ExaWin, NMFX-Exa, ExaStar, WarpX, Exascale, and Pele. And you can see I have a static image or a video of kind of what each of them is about. The first problem, ExaWind, DOE was interested in wind farm simulation, individual turbine simulation, and coupling to larger atmospheric models. That's the ExaWind project. So you can see here's a wind blade turbine. You can see this is much more complicated than just a bunch of squares. There's a lot going on here. NMFX-Exa, they wanted to develop these codes that could scale up chemical looping reactors where you could have billions and billions of particles within a hydrodynamic simulation model these reactors. So, okay, there's particles and these don't look like squares. This is geometry here. So Exastar, we've historically known how to do astrophysics, but they wanted us to take it to the exascale. You can see an image here of, these are 2 merging white dwarfs. WarpX, that's the code that Dr. Schiller mentioned that does accelerator modeling. That's the most famous one that won the Gordon Bell Prize, which some people call the Nobel Prize of supercomputing. So that was a really big deal. They're modeling particle accelerators here. So here we have electromagnetic fields. We have particles that can represent the electrons. Exascale, we have cosmology codes, and there's a cosmology group at Berkeley Lab that uses our code. In this case, there's astrophysical hydrodynamics. There's dark matter, and those are represented as particles. Those particles interact with the grid. And you need to run this at scale. And on top of everything is Pele. We have a suite of different combustion codes, different for different spatial and temporal scales that can do laboratory scale combustion. So here's an image of a hydrogen flame where we're modeling, I think I colored it to be the radical of OH, and then these swirly things I put at the bottom to make it look pretty, or just showing where the vorticity is the greatest. But this corresponds to some tabletop flame, and they want to be able to vary the parameters and the mixture inputs and infer, the efficiency or the emissions from such flames. So this came along with it, and people in our group, and including myself on some of these, who were directly involved in writing these application codes using the AMReX code. And in addition to ECP, just within our group, I have 2 more slides on other things that are going on today in terms of what people are doing with AMReX. So we have funding to study atmospheric flows. So here's a thunderstorm. The actual ultimate goal of this is to couple this with AMR wind. So somehow there can be a notion of how the wind farm interacts with a kilometer scale simulation. That's kind of a newer project. On the right, we are doing ocean modeling studies. So phase 1 of the project, there's this code called ROMS, and phase 1 is to do a rewrite and call it ROMS-X. So it now runs on GPUs, runs really fast. So we have ocean modeling capabilities coming up. So closer to home here with Dr. Schiller, and I'll have a slide on this, we have classically done a lot with fluid mechanics. So on the bottom left is depicted at nanoscale. I think this domain is on the order of a few microns, but fluid jets that pinch and break off, and we want to examine the effect of what thermal fluctuations have to do with this. So this is not a classical deterministic PD. This is actually a stochastic PD that we're solving to study these dynamics. On the bottom right is a new application where we're trying to do characteristics of how these carbon nanotubes laid on top of a CMOS substrate react in terms of their voltage current characteristics. There's a project run where people are actually trying to build a carbon nanotube based photon detector. And they want to be able to say, if I hit this thing with a photon, or if I have point source electrons nearby, what is the response and how do these nanotubes respond? So we're able to, before this, people could model 1 nanotube for a short, small number of microns. And a wonderful postdoc who made this code, and you can see he's got arrays of nanotubes, and he can actually make them so they're not even parallel anymore. And he's been able to characterize, if you're able to theoretically lay out these nanoscale devices on some chip or some wafer, what the response would be. So that paper is actually about to be accepted if they like the reviews. And then one more slide just about what's going on here. We're doing electromagnetic modeling. So here I've taken this resonator. So we have an incoming signal on this input bar, and we want to be able to measure certain frequencies. So as the electromagnetic signal passes through here, this resonator bar is tuned based off the geometry to allow certain frequencies to resonate back and forth. So this is a classical EM model. On the bottom right is a bioreactor example. I don't know why it's flashing, but there we can see particles in here which represent like fuel cells, or fuel for the little microbes to eat and consume. And here we can measure what the fluid dynamics of the system are, where the particles are. We can measure the shear on the solids. We can have solid particles. We can have bubbles in here. This is a relatively new project in the industrial biomanufacturing sector. This is a simulation of current sheets inside of a pulsar. So we have people in our group that study plasma physics. This actually still uses the WarpX code, just in a completely different context. So they're trying to understand how astrophysical dynamics work and how magnetic current sheets are formed and how magnetic reconnection works, because we can only see these things in telescopes and pulsars from light years away. So these are models for how local dynamics on the centimeter scale of magnetic reconnection sheets. This one isn't a cool movie or anything, but we actually have an epidemiological code where you can use the grid cells in AMReX to model different regions, in this case, different counties or different cities. You can have individual particles that represent each individual person, and there's lots of characteristics they have, like whether or not they have disease X, Y, or Z, and how they travel to work or where they go to work, and how they move from county to county, and how they can transmit diseases to each other. So this is called ExaEpi. This is a new project, and it's funny because when you see pull requests come to the repo, it's like adding this disease model, or adding this subway model for how they're getting to work and how often they go to work. Anyway, so I'm not directly involved with this, but I get to manage people who are. And then with Dr. Schiller, Dr. Schiller and Nikhil have visited us twice. At least Nikhil, at least one of their lattice Boltzmann codes is using AMReX. If you want the specifics on how lattice Boltzmann work, there's a whole team of people here, including Ulf, that can tell you more about it. But this is another application where we're trying to extend more to AMReX. You can see, you can still represent the data on a structured mesh. And what Nikhil is trying to do is trying to study nanoscale flows, hopefully with comparison to some of our more deterministic fluctuating models. But there's a whole research effort going on in Dr. Schiller's group, and at least one of them is using AMReX. So I think that's pretty cool.
Two now.
Two, okay. Okay. So at the basic level, how does this code work? Well, you have a structured mesh and you can chop it up and you can do spatial domain decomposition. And once you have your domain chopped up like this, you can assign each individual grid to different MPI ranks, and you can attach each of those MPI ranks to a different GPU. So most numerical methods, the grid data at some point needs to talk to each other. So that's done with MPI. The most common usage is you would exchange ghost cell or halo information between the two grids. You might be able to do some MPI reductions, sum or min-max reductions with this. Sure, particles need to communicate to each other when they cross from one grid or the other, so the correct processor can own them. So there's less communication when the particle needs to talk to the grid. But in all those sense, that's communication. When you're doing floating point work, there's a couple options. So if you don't have a GPU, you could just use your old single core workstation or your laptop. It might even have multi-core, which probably by this point it would have to, but you can use pure MPI just to assign different grids to different MPI ranks and have all of them work in parallel to do their computational work and assemble what information they need to do later. Even if you have a multi-core system and you don't want to have as many MPI ranks, you can use OpenMP shared memory threading if you want. And then finally, if you have one or more GPUs attached to your system, you can attach each of those GPUs to an MPI rank and just make sure all the work stays on the GPU, all the data stays on the GPU, and only bring it back to the CPU if necessary to do communication. So you try to do all your flops on the GPU and let the MPI handle it. So what the advantage of AMReX is, you can write the same piece of code and it will work on anything. It'll work on your old laptop, it'll work on your workstation, some medium-sized cluster, or any of the DOE supercomputers. It's the same code. I've been doing this in the group for whatever, 15 plus years. I've never had to write any lines of CUDA or any lines of MPI myself because the libraries just work, and I call really simple functions that do things for me. If I want to communicate something from one grid to another, there's a really simple function. If I want to have the GPU crunch and do these work kernels on something, I don't have to write anything except a loop that looks like MATLAB. So on the next bullet, I said the code looks relatively simple. It looks like a MATLAB code, but it just automatically works on everything. And not only that, depending on the algorithm, it will scale perfectly fine up to full machines if you need it to. Obviously, if you're doing a PDE that's very communication intensive, like an iterative linear solve, sure, it won't scale as well. But if you're doing explicit hydrodynamics or embarrassing parallel approaches, it just works. So that's one of the reasons why the WarpX code won that Gordon Bell Prize. Now in practice, we don't run our scientific studies that large, as I said. One, because we don't get allocations that big, but it's hard to just do one giant run on a supercomputer because you can't get the time for 24 hours straight. It would burn your whole allocation. So in reality, we tend to run stuff on the 50 to 100 GPU range and run like many simulations because it's too hard just to manage one single simulation and infer science out of it. It doesn't work that way. So, okay, the only code I'm going to show. Let's say I have two big data sets.
Can you dim the lights a little bit? It's just behind you.
This way?
Those, yes, exactly. Yes.
I'll turn it back up. Sorry for the black background. I should have thought it different. Oh yeah.
Thank you.
Two data sets, and I just want to add them together. I have an X and a Y, and I want to add to Z. In C++ or MATLAB, you normally make an array and it would be a 3D array. You define the bounds. Okay, so I skipped a few lines here, but this BA is just it's simply a list of boxes. And it's very easy to assemble a list of boxes that span the entire domain and don't overlap with like one or two simple AMReX functions. But you define this data set, X, Y, and Z. We call them multifabs. Fab is a historical legacy name that stands for Fortran array box, because the precursor version of AMReX actually kept the data in Fortran, and we would call Fortran routines. But now, due to GPU support being on C++, everything is C++. It just, some of the names stuck. So it's called a multifab because there's lots of different Fortran array boxes, but it's really just a bunch of 3D arrays in C++ that are really intelligent, know how to talk to each other really quickly. So yeah, you define your 3D array here. And if you want to loop over all the boxes, you just make this mfiter, which basically says loop over all my boxes, all the boxes in multifab X. Then you extract, okay, what's the box I worry about? And if you're a CPU and you don't own that box, it'll just pass through this and won't do anything. But if you do own it, you have a box, you simply make a pointer into all the data. And then this powerful construct called a parallel for, that's just a triply nested for loop over IJK over the points in box. I could have said 4J equals 4K equals 4I equals and put the lower and upper bounds. But due to this encapsulation, if you take this code and you just type make, and if you're on Frontier, Perlmutter, Aurora, or on your local Linux workstation, it will compile correctly and it will work on the GPU if you want it to. And it literally just does this MATLAB-like thing where you say Z IJK is equal to X IJK plus Y IJK. So this would actually work with maybe one or two lines above it to define what the box array is. And if you make a single C++ file, a really simple GNU make file, and you can just type make and it'll go on all these machines. So it's been made for basic operations. It's kind of dummy proof for simple operations once you kind of just get through the basic weirdness syntax of what these things really mean. But mfiter just means loop over boxes. Parallel for just means IJK loop me over box. Okay. But you get used to it really quick. So okay, next step. It's called AMReX. Why? Because AMR stands for adaptive mesh refinement. This is where things start to get really complicated. So I've shown you a uniform structured mesh up to this point, but now let's say we want to be really efficient. We have some flow feature we want to resolve, and we want to put increased resolution over just this region. AMReX knows how to do this. It knows how to define grids. It knows how to do like the distribution from grids to processors. It knows how to efficiently tell processors to communicate with each other in between levels and at the same level. And furthermore, it knows how to move and adapt grids over time if you simply tell it what you care about. So I can make this Kelvin-Helmholtz instability movie. I can run it single level and it'll work. But if I just write one little routine that says, if the gradient in density is larger than some numerical value, I want you to refine it. Or you could do, if not in this case, if the density is larger than this, or if the temperature is less than this, anything you can code up in an if statement in C++, you can define as the if statement for when you want something to be refined. And it's literally one function you have to write. And if your program is structured correctly, it'll just work and do this with a couple caveats that you need the basic fluid flow equations already established for single level. But you can see that the grids move and adapt over time. So this is very difficult, yet it's still very efficient within AMReX. And it can quickly go nuts, right? If you have thousands and thousands of grids that are moving, AMReX handles it as well as anyone else can. In fact, better, because we have the DOE investment. So here's a compressible multiphase flow where these contours are just tracking where the interface between the fluid state and the solid state is. But you can see the grids are moving where there's increased resolution in certain areas. So all of these communication patterns between levels, how they talk to each other, how to create new grids, how to move things around, how to transfer data, that's all automatically handled within AMReX. So you can take an application code, and if you know the mathematics for how mathematically they need to talk to each other, these things are fairly easily codable. And the framework is just there. So it's super powerful. In addition, there are some core libraries in there. If you have different levels of refinement, you can get really fancy and start to say, okay, I want to be really efficient and I want to advance my coarse grid with the big time step, and I want to advance my fine grid with the small time step, because due to stability concerns, I'm able to do that. And I can save on a ton of computational work because I'm now only resolving in time to a high degree, where I'm resolving in space to a high degree. So this is a very well-known thing, in particular for fluid dynamics, called subcycling in time. So, here my representation of 3 levels. What you do in a basic subcycling algorithm is step 1, you advance the coarse data by 1 time step. Then you advance the medium resolution by half a time step, and then the fine resolution twice by a quarter of a time step. You synchronize up the solution between the medium and the fine to make sure that conservation is maintained or any other physical constraints you need. Then you continue on in a recursive way where, then the fine is advanced, the coarse medium is advanced again, then the fine twice, and then you have to synchronize between all 3 levels. But the point is, you're minimizing the computational work at the expense of needing a few, hopefully cheap synchronization steps between each level, just to make sure that your solution is consistent across levels or satisfies any kind of physical constraints you like. So there are actually libraries in there, particularly for fluid mechanics, that are already built into AMReX, and whole classes devoted to this, because this was born out of applied math efforts from 25 years ago that developed these core approaches. They come for free in there if you like fluids. Okay, other things that are interesting beyond structured mesh that AMReX can support, and I'll breeze through these things. Particle mesh capability, and you've already seen that in some of the videos that, hey, it's not just structured mesh data, there's particles in here too. So, okay, just a laundry list of things. Why would you want to put a particle in a structured mesh code? I'll just list them off, and people can talk to me later if they want deep details. But if you just want tracer particles to blow around in your fluid, just to help you analyze the flow field. You can actually have these particles track what's going on in the fluid as they go around, so they can monitor, what's the state if you care about combustion or chemical kinetics. If you want to model solid particles such as granular materials or complex structures such as DNA or polymers, you can do that. I already mentioned we use particles to represent dark matter in their cosmology code, and they deposit their mass onto the grid, so that can be later used to solve for gravitational calculations. In our warp-X code, whether it be accelerators or plasmas, they represent electrons. They deposit their grid onto the charge, so you can create a current density for Maxwell's equations. I already mentioned in our epidemiology code, each particle actually represents an individual human. And that map of California, he actually runs the model with 40 million particles in it, and each one is an individual person. If you want to do terrain or embedded boundary methods for structures or land features, you can plop them down on the grid and have them talk to your hydrodynamics to tell about the forces you need to satisfy certain constraints. These particles can also talk to each other if they need to know about where they are. In principle, if you really wanted, you could write a pure molecular dynamics code in AMReX and just fine. It's not what it's designed for, but particle class works. You could have billions of particles. They can be distributed over MPI ranks and GPUs, and yeah. On the right, here's an example from the MFIX Exacode where you can see these particles actually represent solid particles as part of a chemical looping reactor, where these particles contain a state about the amount of carbon or oxygen that's on them and consumed as it passes through this process. But this is just an iCanyon video I pulled off their website just to show. It's pretty cool. They're resolving just in this one video. I don't know how many particles are, but you can see there's a lot. Okay, I also mentioned at the beginning, geometry is a problem. A lot of people over the years have developed embedded boundary approaches, so you can take your regular grid and have these cut cell approaches. The advantage here is what you typically do is you use your standard regular mesh stencils in one region, and near the cut cells, you have to develop alternate discretizations that are either higher order accurate or maintain certain constraints. So the code is very increasingly robust to handle these complex geometries. Underlying it is still a spatial mesh. It's just some cells you won't care about anymore if they're completely covered. And then the cut cells, there's a special iterator where you have to kind of fix up or change the discretization just in those cells. But yeah, also a lot of mathematical efforts have gone on over the past like 30 years about how to make these methods robust and stable. The core of these things are these redistribution approaches where you kind of ignore the geometry at first. Then you don't ignore the geometry and you somehow linearly combine these two solutions. So you maintain a certain level of accuracy as well as increase the stability properties, particularly for cells that are really small. So there's a lot of applied math still going on behind that, and that's still kind of an unresolved question. And there have been papers from our group, others are still developing different approaches that they're putting in AMReX to handle these things differently, but it's ongoing work. There's libraries included for other things that we care about. Okay? Linear solvers, if you're trying to do implicit time discretization, or you just care about elliptic or parabolic PDEs, we do have built-in schemes, iterative schemes, if you've heard of multigrid or Krylov methods, and they work. Sometimes if the problem is really difficult, if the geometry is crazy, or your cell aspect ratio is insane, like you have like really skinny grid cells, we will call external libraries such as Hyper or PETSC to just do the linear solve for us. They tend to be slower, but they actually will work for problems where just our more or less basic multi-grid or iterative methods will fail. Increasing FFT support leverages the backends of FFTW for a regular multi-core, a cuFFT or ROC FFT. So we can assemble and do multi-dimensional FFTs actually fairly efficiently now. That's always a work in progress. The communication and data juxtaposition you need to handle multi-dimensional FFTs is definitely a open research topic, but what we have works and it's scales reasonably okay. Built in, we have time integration libraries, but we can also call this external library called Sundials, which has every time integration strategy in the world you could possibly imagine, including multivariate methods where you might be able to partition your PDE into slow and fast time scales and cleverly stitch together and subcycle stiff processes that are cheap. That's an ongoing mathematical research problem that we're involved in. And since the bread and butter of our group was historically hydrodynamics, there's volumes of hydrodynamic schemes and libraries that are also available and freely used, like Godunov approaches, methyline approaches. Those are actually still being developed too, but that's probably got 40 years of history in there of things that just work and we made generally useful for everyone. Python bindings. Another related group of our lab that's involved in WarpX developed Python bindings. So you can actually pass data to and from Python or run the code from Python pure. And the reason is now this opens up, the primary reason was, okay, ML is a big thing, PyTorch is a big thing. So now we can run applications that are coupled with things in Python, applications that are coupled with other simulations. And I'll give you an example later. You can just there's Python binding, so you can stay purely in Python, build the AMReX as a library, and just stay in Python. So there's a zero copy or passing. There's no multiple program, multiple data. This is very powerful for all the AI ML stuff that's upcoming. I'll talk a little bit more about those slides in a minute because I'm running short on time. So I will visualization packages. They're pick your poison. You can use these common supported visualization packages. I won't belabor that for now. So the code, as I mentioned, is open source. There's extensive documentation on the website. Whenever we have some kind of thing that's interesting, I'll say somebody needs to make a really simple tutorial code to demonstrate how to use it. So you can actually clone our tutorials repository on GitHub and has all sorts of examples you can start with to learn. It includes libraries for how to post-process plot file data. The developer base is very active on GitHub. If you post a question on GitHub, someone will pretty much typically answer it very soon. Our Slack workspace is publicly available. Anybody can join, post questions there. It's a very active community and responsive because there's people in our group that are paid to be responsive. So, and then recently, we're now part of the Linux Foundation's High Performance Software Foundation. I guarantee that there are people in this room that know much more about this than me, but using AI, I made this slide and said, why is this a good thing? And they came up with these bullets. So I admit I'd use AI to make this slide, but this is this is apparently a big deal because we're now part of a larger foundation with these sources of support. Now, the elephant in the room, we're not a AI ML group, nor have we traditionally been, but everything about DOE appears pointed toward, you need to start incorporating AI/ML. So over the past maybe 2 years, we've had some level of efforts to do things. I'm just going to briefly overview in the last 10 minutes a few things we've been doing lately, and that might pique some interest here, especially in this particular group. So, okay, a couple of years ago, I had a postdoc who really wanted to learn this stuff. She went ahead and made this and then got a job at Google, just down the street from us. But we have this reacting astrophysics code where the reaction kernel was taking a really long time. And for really expensive networks, it was taking 90% of the runtime. So she's like, I want to train a neural net and replace it. So in the context of doing this, she demonstrated in principle for smaller astrophysical reaction networks, this was possible. And she also developed the interface so you could stay purely within AMReX and simply load a PyTorch model with X inputs and Y outputs and just load it in. So there is now an interface and a tutorial that if you have some kind of PyTorch neural net, you can just export that to a .pt file and read it in later in an AMReX code. Now you can just replace any kernel you want with a surrogate. But we published this in Astrophysical Journal, and I think it's just a few years ago, but it kind of sailed through reviews. Even though I thought that our use case at the end was a little bit weak. We only had a 3-species network, but no one had ever seen anything like that at the time. So this was kind of our first foray into doing something. And even now, some of our researchers in our group are still using this interface to try to replace kernels in our code here. So that was one of the first things we did. Here's an ongoing project where you have a complex flow and so here's flow through a nozzle. I don't know what the viscosity is. There's no really good analytic models, but I can run a molecular dynamics simulation based off the shear rate for an hour or two and figure out what the viscosity is. So what we are doing right now is we're instrumenting our code to be able to figure out when there's enough uncertainty in what the viscosity we need to know is. We can pause the simulation because it's all being held together through this Python interface, run some molecular dynamic simulations, build this Gaussian process regression. In this case, we're actually using a neural net to continually update our model for what the viscosity is based off the geometry and the shear rates you're seeing. And it's this active learning framework where we're actually running in situ AMReX simulations and particle simulations, and it's intelligently figuring out when it needs to pause and run the molecular dynamic simulation to give us a better estimate of what the constitutive properties of this flow are. So the idea is now we only need to run dozens to hundreds of molecular dynamic simulations instead of thousands to pre-build some libraries, since the MD simulations take an hour or two each on a handful of GPUs. So this has all sorts of applications to industrial flows. So we are exploring this right now and developing this framework to do so. So we have a postdoc who's putting together a paper on this. A new project, and there we go. Okay, here's a brand new project. Through the Applied Manufacturing Office at DOE. In microelectronics, they use these plasma chambers depicted on the right to etch patterns onto wafers. But there's a lot of problems in that near the edge of the wafers, the uniformity in how the ions and electrons are impinging upon the wafer you're trying to etch is not uniform. So we have this new project where we are modeling plasma reactors for microelectronics using the WarpX code. And we are trying to have this outer loop optimization workflow where we can vary parameters such as what's the pressure of the system, the temperature of the system, the RF voltage, geometrical features, and we're trying to optimize uniform ion incidence and energy incidence onto this wafer. This is a brand new project that just started. I'm not directly involved in the AI/ML part, but I'm trying to help them optimize, make the simulations run fast. That's my piece in this, but I still get to put the slide on it because it has there's some kind of learning aspect of this whole thing. So this is a brand new project that we're going to be exploring this year. Here's another cool one. There are these new materials that scientists have discovered in the past 15 years discovered that they're useful, called ferroelectrics. And if you stack them together with classical things you would find in a logic device like dielectrics and semiconductors, you can actually make an electrical switch that operates at fractions of a voltage of energy needed for traditional CMOS. So we developed a new code for ferroelectric design, but in order to optimize, the minimal amount of energy needed to have this device switch from the on state to the off state, in our current model, there could be 15 parameters. So for each of these stacks, how thick is it? What are the actual material properties? The actual material scientists can engineer the properties correctly over in the molecular foundry to have them have certain characteristics up to a certain point. But there's a lot of parameters. So what, in conjunction with another visiting team from UTEP, they ran something like 200 simulations, and then they were able to infer from some surrogate, to test out lots and lots of different combinations really quickly to see if they could optimize some kind of design to maximize the energy savings. So that's an ongoing project. Hopefully we can get that paper submitted pretty soon. I'm out of time. Okay, I'm almost out of time. We have some amount of effort into general electromagnetic PDE solvers and finding ways to use AI and ML to make them faster or better. So here's some equations. These are Maxwell's equations describing the electric and magnetic fields. This equation is called the LLG, Landau-Lifshitz-Gilbert equation for micromagnetics. Our original pitch when we were trying to get funding for this is as follows. We know how to solve these perfectly fine, but the problem is when you solve Maxwell's equations, your time steps are really limited because waves are moving at the speed of light. So therefore, you can't take explicit time steps that allow information to travel so far, and you have really tiny time steps. But the magnetization dynamics is what we care about more. So in these magnetic materials, the theory is like ferroelectrics, it's another promising next generation device that allows you to make microelectronic switching logic and memory devices operate at much lower energy levels, because instead of pushing around electrons, you're just manipulating magnetic spins, which is lower in energy. So our problem was we could solve these, but it was really slow. So we were trying to figure out, okay, what angles can we explore to make this faster? And one example was, okay, we just focused on the M magnetization equation first and said, okay, the most expensive thing in this code is this demagnetization solver, which is a convolution. And convolution generically is an order n to the 6 algorithm. So it's very, very bad. You don't want to actually ever do direct convolution. But you can also use a Fourier approach to do convolution, because you can just take the FFT of both signals, multiply them Fourier space and inverse FFT. But even so, it is the most expensive kernel because everything else in the code is just an explicit stencil operation, really dumb and really fast. So we had some effort of just training just to replace this one single kernel. And we were able to use Fourier neural operators to demonstrate we could do it. But the work is ongoing because the speed up isn't so great right now. If you squint, you might be able to say we can run twice as fast. If we scale it up, I think we can do much better because Fourier approaches don't scale very well. But we were able to demonstrate we could get the dynamics correctly. This is ongoing work, and hopefully it will be part of our paper that actually demonstrates our new code package for this Magnex solver. So this is like a kernel replacement thing for something that's really expensive. So that's one avenue we're using to attack this problem. The other one is, okay, I will say I do not understand this slide whatsoever, but a postdoc in our group is working on this, and I've been feeding him data. That's my aspect of this. He's replacing the entire PDE with an ML surrogate, and he's used it on a lot of different problems like Darcy flow and Navier-Stokes flow, Maxwell's equations, electric and heat current transfer. I basically used AI to try to post some bullets together for this, because I know people here might understand these words more than me, but I'm just the data factory for him. And he has an archive preprint on this where he was able to use this diffractive optical neural network to show in principle that he could replace the entire PDE solve with a certain amount of error. Okay, so I think oh good, my timing is good. So just to summarize, okay, AMReX in general, we're a PDE shop, okay? There's tons of applications, and I only listed the ones that actually people in our group are working on. I know we have all kinds of external users. If you look at the GitHub issues, you can see people asking questions from all over, but that's our goal, is to try to be useful and try to allow researchers from across the spectrum, universities, industry, DOE to use our software. We've increasingly incorporating AI ML. We're expecting DOE to care extremely about this. So any future proposals we're gonna go are gonna have to incorporate and take this all to the next level. So you can see some examples of what we've been doing over the past year to try to move toward this direction. But there's endless possibilities, and that is the end of my talk. So I'll take one.
Thank you very much for this great presentation. I think it shows like how computing can really push science and how different areas of computer science can help, developing faster simulations and also better models. I'm sure there are questions.
Yes, I'm sure that the algorithms used in AMReX are quite complicated when you're doing like MPI communication on grids that have different resolutions, and there are ghost cell exchanges, et cetera, et cetera. What have the developers done to ensure the correctness of their algorithms, or the implementations of those algorithms, in C++? Have they used formal methods? Have they used other debugging techniques, or just like hand proofs of theorems, anything like that?
So the developers, okay, everybody at some extent in our group will work on different pieces, but the developers primarily work with application scientists who can help them validate and verify. So it goes back up to applied mathematics perspective. I have some new PD I want to solve. Here's my new coupling strategy. I'll go through all the rigorous stuff. Here's a convergence test. Here's some results compared to benchmark literature. The way it almost kind of works is as we find problems, we work with the pure AMReX developers and say, hey, this isn't working right. And it's a deep debug to show, hey, look, so it's a very collaborative thing. No one can do anything on their own to perfectly validate everything. We like to think our code works correctly in all situations, but it's a forever work in progress because algorithms and users come to us with different things they need. So the pure validation doesn't tend to come from the pure AMReX developer. It's more from the science side, and then problems are reported. These things are so horrifically complicated. If I were to take a combustion code, and even if we're running on 2 levels, sometimes it takes a deep dive to disentangle, is it a bug in my solver? Is it a problem with my formulation? Is it an AMReX bug? And then we have to work collaboratively to kind of figure out what the real problem is. So they can't troubleshoot or pre-advance and test out everything in advance. It's just too hard. But this framework, ECP may have started in 2016, but the precursor software called Boxslide, it's been around since the mid-90s. So it literally has 30 years of development, debugging, and all sorts of, dozens and dozens of people just within our group hands-on on it to try to shake out everything possible. And there's new bugs being found all the time. We just try to minimize that because new features are being added all the time too. So it's kind of a living, breathing thing.
Other questions? Yes, please.
Yes, so I'm kind of more interested in the AMReX framework's introduction of the HPC-IO stack. So you mentioned that there are some applications where MPI communications is much more intensive, and there are some applications that MPI communication is not that level of intensive. So does AMReX actually provides kind of application-aware optimization when running simulations?
Nothing is truly that automatic. In a real world, it would be able to, there's a limited amount of things you can do and some amount of control you can have. Nothing is really all that well automated. So I'll give you an example. In a linear solver, if you want to iteratively solve it, it's just solve a matrix equation. You apply the operator, then you have to do a ghost cell exchange globally. You apply the operator, you do that hundreds and hundreds of times. There are strategies you can use where for that kernel only, you could copy it to a different MPI communicator that has fewer grids that are larger because the computational flops are relatively inexpensive and the communication is heavy, so you can minimize that. But there's nothing that's really all that automatic. We try to have sensible defaults and there's a couple knobs, but that's always a problem. Linear solves forever.